Hi, so today we'll be doing this jump game, and basically we'll be exploring dynamic programming, and to be more specific, greedy algorithm. So for this game, the question here is quite simple. Let's see that first we're given a array of integers, and here in each position, the number here indicates the maximum steps or lengths that we can jump. For instance, know that in every test case, we start from the first element, like this one, index equals to 0, so the first element, and then since it's 2 here, which means that we can jump 2 steps or we can jump 1 step. So for instance, we can jump to this 0 and we can jump to this 1, but we cannot jump to this 3 since this takes 3 steps, right? So the same thing applies to here. So for instance, we jump to this 2, then at this point we can jump to this 0 and we can jump to this 3. And if we decide to jump to this 0, then we cannot move anymore since it's 0 here. But if we jump to this 3, we can jump to this 2, we can jump to this 1, and we can even jump to the last one. And the goal here is that we want to know whether we can, like, by jumping through the elements, whether we can reach the end element, the last one element. So we return true if we can reach it, and or otherwise we just return false. Alright, so here's the question, here's the problem, and here's how we come up with the greedy algorithm. Basically, in this case, the basic case, the basic procedure is quite simple. We just decide the steps we want to jump from the point where we are now. And so talking about the greedy algorithm, that we just want to jump as further as possible at each movement. We just want to reach the farthest element that we can reach at this point at each jump. So for instance, when we start at this 2, we definitely want to reach the farthest position we can ever reach. So at this point, we can decide to jump to this 0, we can decide to jump to this 2. It seems like this 0 is further away from this 2 than this 2. But actually we should not jump to this 0, since we need to consider how far can we jump again just after this jump. So if we jump to this 0, we cannot jump anymore from this 0 position. So the point that we end up with is just 2. But if we jump to this 2, we can then jump 2 steps again, since it's 2 here. In this case, we end up jumping 3 units, 3 steps. So 3 is larger than 2, which means that we need to jump 1 step. We need to jump to this 2 instead of to this 0. And the same idea just applies again until the end case is that whether we find that the last element is within our jump range. For instance, if we reach this 2 and we see that if we jump just 2 steps, our jump range can perfectly cover this n0, then we know that we can indeed reach this last element, so we return true. Or otherwise, we find that we're stuck at a 0. For instance, somehow we're stuck in the 0 and we cannot jump anymore, which means that we can never reach the end element, so we just failed. However, I know when I first look at this question, I may had a question doubt about this approach, since what if, let's see, what if between for instance, what if between these two there's a very large jump, and if we just decide to jump as far as possible to these 2, then we may miss this chance of jumping very, very far. So actually this explains why I said that what I mean by jump as far as far away as possible is not just you looking at the current jump, but you combine the current jump with the jump length you can get after the current jump is made. So this really avoids this problem, since in this case we will definitely decide to jump to this 10. Since though we only choose to jump one step at this length, it seems like we can jump 2, but if we decide to jump 1, then we can get a 10 after this jump has been made. So 1 plus 10 is 11, and it's a huge jump actually. Alright, so let's start with the coding. So let's do coding. So initially we get an index. We want this variable I to store the index. And while I is smaller than num-star length, we do not want it to go out of the boundary. So if I plus nums I is larger than or equal to num-star length minus 1, then we just simply return true. Right, which means that we know that at this current position, our jump range can cover the target endpoint, so we just return true, since the target point is absolutely reachable. And then if it's not reachable yet, then we need to find like which jump should we make, like how many steps should we jump. So we just go through all the elements that we can jump onto. I plus 1 and j smaller than j smaller than or equal to I plus nums I, and then j plus plus. Note here we actually need another variable to store the maximum distance, the maximum jumps we can make, and also we need a variable to store like the position that we end up with. So here, so if j plus nums j, like we want to see like after this jump, and then we directly make the longest jump that we can make from the point we landed. We want to see which one is the farthest. So if this one is larger than the max, then we update the max, and also we update the point that we will be landing on. So next equals to j. And if, how can we find that we're stuck in here? So for instance, if the current position is already 0, so j equals to I plus 1, but the maximum is just I, right? So we won't even get into this for loop, then the max will end up with 0. Or for instance, the points that we can reach when we so in this case we will get a 0, and only in this case we see that we're stuck here and we're done, that there's no chance for us to reach the target. So if max is still 0, then we return false. Otherwise we just update the I for the next iteration of this while loop. Just this tells us that we have indeed jumped to the point that we decided. And lastly, actually this while loop is enough, since we will either just end up with a true or with a false. But talking about the syntax, we just need a return type here. So we just can put a false here, or we can put a true. It doesn't matter. So we just submit our code, and let's see. Right, so it's correct, but it's not fast enough. Now I will tell you another. First let's just okay. So here I will tell you another greedy algorithm. It's quite similar, but it's faster than this algorithm. So now let's think about this question from another angle. So we are still using the greedy algorithm. So in this case, we want to just record the farthest position so far that we know we can reach. And then we just simply go through each element just one by one from index equals to 0 to maybe finally the target. We want to see if we want just go through the element one by one and update the farthest position ever just so far we know that we can reach. If during the iteration we find out that our current position is not reachable, which means that so far the farthest position that we know we can reach is smaller than the current index in this iteration, which means that we know that we can never get here. If we can never get to a position before the endpoint, this tells us that we cannot even just we can never get to the endpoint, and game over, and just we're down here, so we can return false. Otherwise, once we know like the farthest position we can reach is larger than or equal to the endpoint, then we just return true. So here we just write the max position we can reach here first is just the 0, and then for each element in the array, so for int I equals to 0, I is smaller than num star length, and I plus plus, if, so we can just update it, so max equals to max star max or I plus nums I, and so before that we want to see whether it's reachable. So if I is larger than max, then we just simply return false, since we cannot just get into that point ever. And the largest reach is here, and if we find that actually we can just leave the for loop here and we can return true. Since if the endpoint is not reachable, we will somehow at some point we will get a return false, but we can just let this program be more efficient. So if max is larger than or equal to num star length -1, then we can just return true. And lastly, in order to fulfill the requirement of the syntax, just put a return true here, and let's submit the code. Right, see, we're much faster than the previous one. And let's analyze the time complexity of the code. So for this code, it's clearly just one loop to go through all the elements, and it's basically so the time complexity here, is just O n. And if we look at the previous one, this 46 millisecond one, we can see that actually the time complexity is still O n, since we are basically just going through all the elements. Just we go to this element, for instance, we just start with we start with the first element, then we check the following two elements, then we decide this one. From this one, we check the following, we check the following, we check the following, and until we land with this, we land on the we ended up with the target, the endpoint. So this algorithm is also the time complexity is also O n. However, why the second algorithm is slightly faster than the first one is, first, each iteration in the first one is more costly. So we can see there are more comparison, there's more calculation here. So clearly each step is more costly. And besides, the first algorithm includes some duplication, some redundant steps. So for instance, in this case, let's see that if we start with the 2, so we first check this one, we also check this one, and then we decide to write down the 10, the second element in the array. Then for this 10, we need to check this one, we need to check this one, we need to check this one, and everything behind it, right? But note that this two, like this two, is circled by the blue one, but it's also circled by the red circle, which means that we have checked this twice. And you can see this actually can happen for many times in the first algorithm. So we have made many redundant iterations. So though it's still O(n), but it's not that efficient than the second algorithm. And talking about the space complexity, they are both O(n). They are both O1 since they just contains finite numbers of additional variables. However, I believe that the second one should be more should consume less space. Let's see, right here you can see the second one consumes less space, and I think it's just quite intuitive. You can just look at how many additional variables each code creates. And so far that's all for today's problem, and see you in next video.